Okay, today we're going to talk a little bit about circular motion. And before we do, let's talk about radians. So when we do circular motion, we want to measure the angle in radians rather than degrees. And just a reminder to you, when the angle theta equals 1 radian, that occurs when the arc length s and the radius are the same. So when s equals r, that's an angle of 1 radian. Now, generally speaking, the arc length equals the radius times the angle in radians. That works for any angle. Now, let's take a look at a very small angle, d theta, and a very small angle, ds. Arc length, ds, I mean. This means that ds is going to equal r d theta. Okay, now, I have a rubber stopper here on the end of a string. I'm going to spin this around, and let's assume this is a vertical circle, and the rubber stopper is moving at a constant speed. Now, you might be tempted to say the rubber stopper is not accelerating because it's moving at a constant speed. But remember, acceleration is not just speed, it's speed and direction. Even though the rubber stopper is moving at a constant speed, it's constantly changing direction. It's not moving in a straight line. So let's take a look at that. So here's the path of the rubber stopper, a circle. And I'm going to take a look at the velocity of the rubber stopper at that point. It's always going to be tangent to the circle. And then a very short time later, we have a different velocity, v2, also tangent to the circle. Now I'm going to draw a radius from the center to the tail of v2, and they make a right angle with each other. Now what I'm going to do is I want to find how much the velocity changes between v1 and v2. And it's going to change an infinitesimally small amount. So I'm going to call that dv. I know that dv is final velocity minus initial velocity. Now, because the rubber stopper is moving at a constant speed, we know that the size of each velocity is the same, all right? But the direction is different, so there's going to be an acceleration. So what I'm going to do is I'm going to take this vector v1, I'm going to flip it 180 degrees to make it negative v1, and I'm going to add it tip to tail to v2. And it should look something like this. Now, dv, the change in velocity, would be the resultant vector of v2 plus negative v1, which is drawn from the tail of the first vector to the tip of the second vector. Now notice that dv is right along the radius, which means the acceleration, or the change in velocity, is toward the center of the circle, which means the acceleration is toward the center of the circle. It's called the centripetal acceleration. Centripetal literally means center seeking. It's also called the radial acceleration because it's along one of the radii of the circle. All right, so let's take a look at this. Now, this triangle that I drew here has an infinitesimally small angle, d theta. We know that dv is going to equal either v2 d theta or v1 d theta. And since they're the same size, I can just say v d theta. Okay, so the change in velocity is v times d theta. Now, what I'm going to do is I'm going to come back over here and I'm going to solve this for d theta. Right? So d theta equals ds over r. I'm going to replace d theta with that. Okay, and I'm just going to rearrange the terms a little bit here. So dv equals v over r times ds. Now I'm going to divide both sides by dt. And we all know that dv dt is acceleration. And we all know that ds dt is velocity. So acceleration equals v over r times v. Or I can rewrite it like this. And this is the centripetal acceleration. So if we use this equation, it gives us the size of the centripetal acceleration, right? Because v is squared, it's always going to be a positive number. But we always know that the direction is toward the center of the circle. And this is either called centripetal acceleration or radial acceleration. Two words that describe the same thing.